Okay, so we are going to integrate over a piecewise smooth curve this time, so not a full-on smooth curve, just to show you what needs to be done in this case. It's not hard, it's just a little more work, that's all. So C is going to be the straight line path from 0 to 1 plus I, followed by the straight line path from 1 plus I to 1 plus 2I, as you can see in the picture. So let's go in, and I'm going to go in and label these pieces. So C is made up of two pieces, C1 and C2. So C is C1 union C2. And to compute this this contour integral, which, I know this doesn't look like there's no z's here. If you want, you could have written integral over C, real part of z squared, plus I, imaginary part of z squared. Don't do this, but if you wanted to make everything in z's, you would do something like that. So to compute the integral over C, what we have to do something we did in the last section. We integrate over C1 and we add that to integrating over C2. And I'm not going to put the arguments there, but we integrate over C1, integrate over C2, add those together. That's the integral over C. All right, so let's start with C1. So we first need to parameterize C1. Now, luckily, there's always, in fact, let me just say this now, this is a parameterization that you should just know how to use and know the formula for. There's a handful of shapes that are easy to parameterize, and the easy ones we should know how that works. Straight lines are perhaps the easiest possible things to parameterize. So the parameterization of the segment, the line segment, joining z1 to z2 is z of t is 1 minus t z1 plus t z2, and this is on the interval from 0 to 1. So notice this is a linear function of t, so the resulting shape will be a line. There's no quadratics here or anything like that. Linear functions produce lines. When t is equal to 0, the left endpoint, the z2 part vanishes, and the coefficient of z1 is just 1, so you just get z1. Okay, we start off at z1. And when t is equal to 1, the coefficient of z1 vanishes, and the coefficient of z2 is 1, so we just get z2. This is perhaps the easiest possible parameterization in existence. Know how to parameterize a line. It's not hard. You just do this. Okay, so don't put it on a pedestal. It's not hard. Just write this down. Okay, so for C1, we're going to parameterize from 0 to 1 plus I. So our starting point is 0. Our ending point is 1 plus I. And that's on the interval from 0 to 1. The 0 goes away, and we just have t times 1 plus I, 0 less than or equal to t less than or equal to 1. Let's actually multiply that in. That's t plus ti, 0 less than or equal to t less than or equal to 1. So that's our parameterization. In particular here, our x of t is t, and our y of t happens to also be t. Now we could have gleaned that from the picture pretty easily, but I wanted to remind us how to parameterize line segments because it's a very simple thing and very important to remember. A lot of our examples will be built with line segments. Okay, so let's integrate now over C1. And the argument was x squared plus y squared dz. So let's go ahead and let's plug in our z. So we get integral from 0 to 1. X is t, y is t, and I guess if this is our z, dz is differentiate each of these, so that's 1 plus I dt. Great. Now, what do we see here? Well, 1 plus I is a constant, so I'll move that out front. And then we have 2t squareds. So really, I can move the 2 out front as well if I wanted to. It doesn't actually help, but if I wanted to, I could do that. It's my video after all. An antiderivative of t squared is 1/3 t cubed, evaluated from 0 to 1. When we plug in 0, it's going to annihilate it. 0 is the great annihilator in this case. So we just have to plug in 1. I'm just going to emphasize that when we plug in 0, we get nothing. So let's see here. I believe what we get is, did I miss something? I think I missed something. Ah, there's an I on the y squared. Okay, we all make mistakes. Dang. Okay, let me fix this. I don't have the energy to re-record this, so. All right, bummer. That's okay. So we're integrating t squared plus I t squared. All right, I thought something was awry. All right, an antiderivative of this, we're just going to do it all together, is going to be 1/3 t cubed plus I 1/3 t cubed, evaluated from 0 to 1. Again, 0 is still going to annihilate everything, so we just have to plug in 1. So let's plug in our 1. When you plug in 1, you just get the coefficient. So we get this. Oops. And then I will emphasize that when we plug in 0, we get 0. Okay, we can make this look a touch better, I think. There's a 1/3 in both those terms. And when we pull out a 1/3, we're left with a 1 plus I. So there's actually two 1 plus I's. And I believe what you'll find, when you, oh shoot, dang. I messed this up ever so often. One more time, sorry. This 2 should not be here. Okay, now it's correct. I am so sorry. But let's see. When we square 1 plus I squared, I believe what we'll find is that's going to be 2I, so we get 2/3 I. All right, sorry for the mistakes. Okay, cool. So that's the first integral. Now let's do the second. So C2. All right, let's go back up and remind ourselves the parameterization. So 1 minus t start point plus t end point. Our start point's 1 plus I, our end point's 1 plus 2I. 1 minus t start point plus t end point. And that's on the interval from 0 to 1. All right, I'm going to have to plug things in here. So I'm going to go ahead and separate this into the real and imaginary part. So we're going to multiply the 1 minus t into both of these. So we get 1 minus t plus 1 minus ti. And I'm going to go ahead and multiply the t into both of these. So that's going to give us t plus 2ti. And let's see, if we combine the real parts, 1 minus t plus t is 1. And 1 minus t plus 2t is 1 plus t. All right, so our parameterization is 1 plus 1 plus ti. And that's on the interval from 0 to 1. Now again, we didn't have to use the straight line parameterization. We could have just said, hey, my x-coordinate has to always be 1 if I'm going to stay on this vertical segment, and my t value needs to increase from 1 to 2. So you could have used 1 plus ti, where t instead varies from 1 to 2. It has the same effect. All right, let's now compute the integral over c of x squared plus I y squared. I'll get it right this time, dz. And so that's integral from t equals 0 to 1. Our x coordinates 1, and then our y coordinates 1 plus t. And dz, when we differentiate the 1, we're going to get 0. When we differentiate the 1 plus t, we're going to get 1. So our dz here is simple. It's just I dt. Just write it. dz is 0 plus 1 times I dt. Cool. So let's multiply some of this out. In fact, I'm actually not going to do that. I'm just going to multiply the I into both terms. It's going to make this guy a negative 1 plus t squared, and it's going to make 1 an I. Great. Now, this is not just, it's not t squared, so I mean, technically we should do a u substitution, But this is a linear change of variables where the rate of change is constant. Well, it's 1. So in fact, an antiderivative is just going to be negative 1/3 1 plus t cubed. If you don't believe me, differentiate that. And then ti, because there's a 1 here. And that's evaluated from 0 to 1. 0 is actually not going to be the annihilator this time. We're going to get something non-zero from the first one. So let's plug in both of our bounds this time and be careful. And then minus 0 times negative 1/3 1 plus 0 cubed plus 0i. Great. Oh, shoot. And so that's what? 2 cubed, that's negative 8/3 plus I. And then minus negative 1/3, I think, is all we get from here. So that's positive 1/3, so we get like negative 7/3 plus I, if I haven't made any further mistakes. Negative 7/3 plus I. Okay, cool. So that's the second piece for our contour integral. So the integral over c of x squared plus I y squared dz is the integral over the first piece, x squared plus I y squared dz, plus the integral over the second piece, x squared plus I y squared dz. The second piece we just computed to be negative 7/3 plus I, and the first piece I believe we found to be 2i/3. Let me just go back up real quick though. Yeah, 2/3 I. So let's see, if we were to combine these, we get negative 7/3. We have 2/3 I we add, so I think that's 5/3 I. So I'm getting negative 7/3 plus 5/3 I for the value of the contour integral over this piecewise smooth curve. Now again, we did these in the last section. We did these problems where you have to break it up over some pieces, and it's the same thing. The only thing that's different in this section is we have this dz that we have to transform, and then we have to carry out some complex arithmetic. That's the only thing that's new.